So, what's the deal with the angle brackets anyway? We've been using them all semester. They clearly are pretty important. So if we want to parameterize a vector, if I want a vector of int or a vector of float or a vector of string, I need to use those angle brackets. They are the one thing we weren't able to add to our vector class earlier this week. And we've just seen that we can also use angle brackets when we call functions. So we noticed when we call the makeShared function that we use angle brackets, and that just like with a vector, well, what we put in the angle brackets is the name of a type. So it's finally time to figure that out. And we will start with this exercise. It actually takes us back, I think, to the very first week. And certainly it takes us back to the first time that we discussed function overloading. So I have here three vectors, v1, v2, and v3, a vector of ints, a vector of floats, and a vector of strings. And I would like to print out my vector of strings. Let's take a look at how the code works as it's written without my print function for a vector of strings. We can see it prints out my vector of ints and my vector of floats, so v1 and v2. The real exercise here is to write a new version of the print vector function that can handle v3. So I want to print out my vector of strings. But then I want to think very carefully about the precedent that I'm setting. If I have to keep writing print vector functions for every new vector that I come up with, maybe I'm going to end up with a lot of work in the long run. But we'll just start with task 1 and see where that takes us. So we'll scroll up. Okay, so here's my print vector function for a vector of ints. And here's my print vector function for a vector of floats. And if we stare at them for a minute, we will notice that indeed they are different. So the compiler does need two different functions here because one takes a vector of ints and one takes a vector of floats. And although it's valid to pass in an int where the function requires a float or vice versa, you can't simply convert a vector of ints to a vector of floats. So you need a separate function for each of these two vectors. And I can prove this. I can say, well, the compiler can't see its way around what I'm doing, even though the functions happen to be identical. It does care what the argument type is. I can't just try and pass in a vector of strings and expect the compiler to figure it out. So I have to write my own print vector function that takes a vector of strings. Okay, so we'll copy and paste this one. We will literally copy and paste it. We'll observe that the core of the function is basically identical, so it's for each element of the vector v, but because I use the auto keyword, this for each loop really doesn't care that much whether the elements are ints or floats, but certainly in the function signature, it's a big deal that I specify that I'm taking a vector of strings. All right, so we'll try that out. And as usual, we should have some instinctual aversion to copying and pasting code. Occasionally, a little bit of duplication is warranted. We saw that last week with those constant functions. We actually saw that earlier this week with our vector when we had to make two versions of the .at function and two versions of the square brackets operator. Not the most palatable thing in the world, but maybe manageable if there's only going to be two of them. And so now I have a function that can print out a vector of strings. Great. But I realize if I want to print out vectors of more things, I'm going to have to write more variants of this print vector function. And it doesn't seem reasonable that I have to keep even calling these things variants. They're basically just the same code over and over again. And there are lots of vectors I might want to print out in life, not just vectors of ints or floats, but unsigned ints, or not just strings, but types that I've made up myself. In fact, I might want to print a vector of anything where the elements can be printed with the usual stream insertion operator. So what do I do? Well, I suppose we should first try and tackle this with what we already know. I could say, well, although this duplication is a little bit scary because the more copies of the function I have, the more work I will have to do if I need to fix it or modify it later, I suppose it's not that bad because all I have to do is copy and paste it. So what I could do is I could say, well, I don't know any way around copying and pasting it, but I could leave some instructions to create a new variant. So if I want to, if somebody comes along later and wants to print out a vector of something else, I could leave them some instructions to be able to create their very own print vector function. So let's see, what are my instructions? Copy and paste the code below. And then I will paste some code here. So here is my basic print vector function. But I want to make it so somebody could make a print vector function for any type they want, not just a vector of strings or a vector of ints or a vector of floats. So I will leave them some instructions. I'll say, okay, what we'll do is we'll just say this is a vector of something. We'll just call it T for type, the element type of the vector. And I'll tell them, copy and paste the code below, replace all occurrences of T with the element type of the vector. Okay, great. So now I've written the print vector function once. I've tested it. I've proven that I can print vectors of strings or ints or floats or probably anything that I can push into my output stream. And so if somebody comes along later and they have their own vector of something that isn't a string or an int or a float, I have left them some nice instructions for how they can copy and paste this print vector function to make a variant that works for them. Well, I mean, that's better than nothing. I don't like the duplication, but I suppose these are pretty concise instructions. What I've given them, in a sense, is sort of a template. I've said, here is the basic structure of my print vector functions. All you have to do is sub in the type of your choice for this placeholder t, and you've got a print vector function that works with whatever you want. Okay, great. Is that really programming advice, though? I mean, I just wrote a comment in a piece of code. I basically wrote prose. The compiler doesn't even care about this. I've left instructions to a future programmer. And in doing this, I'm first off assuming that the future programmer isn't as grumpy about this as I am, even though usually with my own code, the future programmer is me, but also that the future programmer is competent enough to actually read these instructions and follow them. And there's another problem, too, which is that when people are working with vectors of stuff and they want to print it out, they're probably more concerned with what they're working with, their vector, than trying to figure out how to implement their very own print vector function. And finally, aren't these instructions simple enough? I've defined this template. I've said all you have to do is copy and paste your own type over the placeholder t. Isn't this such an automated process that I could ask the compiler to do it for me? Well, now you can. It turns out that the C++ language supports adding your own templates for functions or classes where certain details are left out, where instead of a particular type or value, you have left in a placeholder that the compiler can fill in later. So instead of having to write my own set of print vector functions, I can leave the compiler a note about a template for a print vector function that it can use as needed. Whenever it needs a print vector function, it can just fill in that placeholder for you, and presto, you have a print vector function for the type of your choice. So instead of leaving these instructions to a human, let's leave instructions for the compiler. So what I'm going to do now is I'm going to delete all of my print vector functions and work only with this template. So what I want to do is tell the compiler, hey, this letter T here is a placeholder. So it's not a real type. It's meant to be something you fill in later when you need the print vector function. So I'm going to do that by adding this directive before the function signature. Template, and there are the angle brackets, template type name T. Now, to be clear, this template directive is part of, we can think of it as being attached to the function signature. And in general, when you have a template directive before a unit of code, that being a function or a structure or a class, the template directive applies to that entire unit of code. So in this case, you have a function with curly brackets and a function body. Everything inside those curly brackets and the function signature can now use this type name T as a placeholder. By tradition, we typically put template directives on the line above the function signature. But to be clear, you can think of it sort of as part of the function signature. So really, you could write it all like this. But you'll see in this course, I always write it with the template directive on a line above. What this is doing is telling the compiler, in the unit of code you are about to see, this print vector function, I am going to use an imaginary placeholder type called t. And that means when you compile the function, whenever you see t, don't worry about it just yet. Later, if ever I use the function, I will tell you what I mean by t. And then the compiler can go through and figure out if t makes any sense in that context. And before I go further, let's just see what happens if I compile this. So I'm going to try and cram all of this onto one screen. Okay, so I've got my templated function, and I've got my 3 calls to print vector. Notice that when I use print vector, from the point of view of the programmer of main, I don't see any angle brackets or anything. And we've observed already that certainly the angle brackets have some relation to templates. This is the first time we've seen angle brackets in expressions like this all semester. We've used less than and greater than signs, but never have we seen types enclosed in angle brackets until now. And it compiles. And it runs. And so what's happening here is I've told the compiler, here is a template called print vector. Print vector takes a vector of something, we'll call it t. And if ever you need to call print vector, you, the compiler, can try and figure out what I mean by t. And the compiler on line 24 says, okay, so you're calling the print vector function. You've already told me that print vector is sort of incomplete. It's missing a type. Let's see if I, the compiler, can figure out what you meant. Well, let's see. You're passing in v1, a vector of int. And you're taking a vector of t. t, the placeholder. So you gave me a vector of int, and you're taking a vector of t. Hey, wait a minute. Maybe you want t to be int. And same thing down here in line 25. You give it a vector of float. The function expects a vector of t. The compiler figures out, oh, you're telling me that t is supposed to be float in this case. And then finally for v3, you're telling it that t is supposed to be string. And so what's happening here is what's called type deduction. You've defined a template, a generalized version of the function that can work with any types. And the compiler will compile this. It'll accept this function from you on the grounds that when you finally try and use the function, it will figure out what you meant. And then when you call the function, in this case, it can deduce what you mean. You give it a vector of float, and the function expects a vector of t, then the compiler figures out, oh, I see, you're trying to tell me that t is supposed to be float in this case. Every time you call print vector with a new element type, it compiles a brand new version of the print vector function for you with that type. In a sense, the compiler is doing the exact copying and pasting that I was doing earlier. So in this code, because I've called a print vector with 3 different element types, the compiler will actually prepare for me 3 different compiled versions of the print vector function, because the types of the vector's elements are significant to how the code runs. It isn't able to run one single version of print vector for all 3 element types, but it is able to automate the process of copying and pasting the function by using this template directive with, you can think of this as a template parameter, a form of parameter for the function. And I'll come back to that at the end of the video. So we've defined a parameter that is a type name called t. In general, though, you can create templates with as many parameters as you want, and you can name them more verbose things than just t. Traditionally, when you have a template with one type parameter, it is often just called t, just like we often use I for a variable of type int that has a very short lifespan. Okay, so there's one use of templates, an example of type deduction, where the caller of the function may not even know that templates are being used. As far as they're concerned, there's just some magic happening. And when they call the function, magically, the function's able to work with whatever element type they provide. We'll see in a few minutes, there are cases where you have to use angle brackets when you call the function because the compiler isn't able to deduce the type that is meant to be the placeholder that exists in the template. But first, we'll go on to this one. So here I again have my 3 vectors, v1, v2, and v3. And I will just try compiling this to show off what it does. I think maybe the name of the function makes that somewhat obvious, but just in case. So this is called template functions 2. We'll run it. Okay, so I've got this function called second to last, and it takes a vector and it returns the second to last element. So in the case of v1, that would be 10. In the case of v2, that would be 11.6. In the case of v3, that would be the word raspberry. And in all cases, of course, the type is different. The second to last element of v1 is going to be an int because the elements of v1 are ints. The second to last element of v2 is going to be a float because the elements of v2 are floats. So in this case, the return type of the function that I'm calling differs depending on what I passed in. It's not just a matter, as it was in the previous example, of using a placeholder for the argument type. In this case, I will have a placeholder that will be my return type and maybe something in between. And so the goal here is to write the second to last function for my vector of strings. In this case, because we've now heard of this idea of defining templates, the prompt doesn't really beat around the bush here. It just says use a template. Don't bother trying to copy and paste first. Don't waste effort with that. So here are 2 versions of the second to last function. And I think 2 versions should be enough to show us what we have to change, what we want to make a placeholder that can be subbed in later once I know what element type my vector is going to have. The second to last function that takes a vector of int takes the vector of int, and then it pulls out the element and puts it in a variable. Now, I agree, frankly, that you probably would do this as a one-liner. You might just write return v.at v.size minus 2. I guess I'm going to claim I'm doing this to prove a point. It's valid to do this, though. I'm storing the element in a variable, then I'm returning that element. And of course, the return type is int. Down in the float version, it takes a vector of float, it stores the element in a variable of type float, and then it returns a float. So what I want now is to make a generalized version of this, because we can stare at this and realize that this will work for literally any vector that has at least 2 elements. Doesn't matter if it's ints or floats or strings or anything else. As long as the vector has enough elements, you can find the second to last thing. Because the vector is able to be flexible with types, why can't we write a function that's flexible with types as well? So what I'm going to do is I'm just going to adapt the int version to be my templated version. I'm going to say, what do I do to generalize this to work with any type? Well, first, I'm going to use a placeholder. I'm going to say, well, let's make up a type name, so we'll call it t, which is a placeholder for the actual element type of the vector. You give me a vector of t. And then when I pull out the element, well, let's see, a vector of t, if I pull out a specific element of it, that will have type t. And finally, when I return an element of a vector of element type t, obviously that will be type t as well. Notice in this example, I am using my placeholder in more places than one. I'm not just using it in the function signature as an argument type. I'm using it in the middle of the function to refer to it the type of a variable, and I'm using it as the return type of the function. In general, inside of something with a template directive attached, you can use t just like it were any other type. When the compiler actually tries to use the function, it will verify that your use of t is appropriate. So an example being, I'm allowed in my function to try and construct a new variable, so I'll call this test or something. I could construct a new variable of type t. And this is fine. The compiler will let me try this. When it compiles the function, so later when I try and use the function, it will go through and verify that, the type t does have a default constructor that I'm allowed to call. But in general, when I'm using a placeholder, I can just use it like any other type. And it's only later when I try and call the function that it verifies that I am allowed to use it that way. I think, though, that this use is pretty good. I think that for most types that I might have in my vector, all of these operations are valid. Certainly I can make a vector of type t, and almost certainly I'm allowed to copy an element of the vector into a new instance of t. There are types that don't allow that, but most types do, and then I'm allowed to return something of type t. So now that I have that, we'll first see whether I can call the existing formulations of what I already have in main using my new templated version of the second to last function. And sure enough, I can. And in fact, I guess I already uncommented it, we can see we can also call second to last on the vector of strings. And so in this case, I was able to define my templated second to last function that uses a placeholder and therefore can accept vectors of anything. And we notice the placeholder has to get used all the way through, because of course if I take a vector of strings, I don't want to accidentally store the string into an element of type int. If I did that, I would get a pretty predictable error, the usual error that you get when you try and pass something in, when you try and store a string into an int. And so we can see, let's scroll up and see about this. So it's saying, sorry, you gave me a vector of, actually this one is complaining about the vector of float, which is a good point. Obviously a vector of float, you don't want to store that in an int either. This is giving me the usual error about uniform initialization. You can't initialize an int using a float. And here we can see, yeah, it's still complaining because it doesn't understand exactly how to convert. You store the string in an int, that's already a problem, and then you try and store the int back into a string to return it. And so that's one reason why you need to make sure you use t all the way through. And in general, if you are writing a templated function and you get bizarre cryptic errors like this, especially errors that say things about conversions, cannot convert, could not convert, then that's a sign maybe you've forgotten to use your placeholder type in one or more places. Okay, so I'll compile that again just to resolve the tension there, to make sure we know that we have a working implementation. And we'll just run it again. There it is, and we can get the second to last element of each vector. I'm noticing now all three vectors have size 3, which does seem a bit creepy. So just to make sure we can prove that this will still work on vectors of length 4, let's see what happens if I try adding an element to my string vector, and then sure enough, now the second to last element is pineapple, and the function still works. Okay, one more example. So I've got my templated print vector function here from before, and now I want to convert a vector from one type to another. Now I've deliberately written out these conversions not as a single initialization assignment, but as both an initialization and an assignment statement, because I'd like to make a certain point about a trap you can fall into with this logic. Because basically what I want to prove here is that the way the compiler works with templated functions is really no different than how it works with any other kind of function, how it figures out which function to call when there are multiple functions with the same name. Okay, so I'm going to begin by just showing off the code that I already have. So what I have so far is a vector of type int and a vector of type float. And what I would like to do is I would like to take the vector of type float and convert it to be a vector of element type int. So I take my vector v2, which is a vector of float, and I have a vector of int, and I call this function convert vector. Convert vector, in this case, will take a vector of float, convert it to a vector of int, and then return it. And then I store I make a copy of that and store it in this vector iv2. Run that, and we can see there it is. So my vector floating point values is 10.6, 11.6, 10.17. We know that when we convert floats to ints, they get truncated, so we get 10, 11, 10. So let's take a look at the convert vector function. Okay, so I've written a few different overloads of convert vector here. Here's a version where I pass in a vector of int and I get back a vector of float. Here's a version where I pass in a vector of float and I get back a vector of int. Now, although I could use auto here, for certainty, I'm actually using int as the element type of the input vector. So I create a vector of float, I then iterate over every int in my input vector, and I just add it to the result vector. And we should understand that because the result vector has element type float, if I try and push in an int, the compiler understands to coerce that int into a float. Same thing down here. If I take a vector of float, I will first make a result vector of element type int. I will iterate over all of the floats in my input vector and just push them into the result vector, which automatically converts them to type int. Okay, great. So I can do that, and we can see the conversion works. What do I want to do next? Before I create any templates, I would like to try and do this with just regular overloaded functions. So I would like to, instead of converting from a vector of float to a vector of int, I would like to convert from a vector of float to a vector of unsigned int. So I'll try exactly the same formulation that I have above. I call convert vector on v2, and then I store the result in my vector of unsigned int. And I pass in v2, and I expect that this convert vector function will return a vector of unsigned int. Okay, now first thing, we can't already do this. Whoops, well, I have to save the file, and then I'll prove my point. I try compiling after saving. Yes, now the compiler complains. And so I try compiling. It says, sorry, I have no idea how to do this. I don't know how to make a vector of unsigned int out of a vector of float. The errors it's giving, we can see they're sort of neither here nor there, but maybe it's because I haven't defined an overload yet. So I've got an overload that takes a vector of float and returns a vector of int. Maybe the solution is to try this. So I write a version of the function that takes a vector, and we try to ignore this comment for now. I write a version of the function that takes a vector of float and returns a vector of unsigned int. Well, why don't I just try that? Then I can convert a vector of float to a vector of unsigned int. And so I made sure to save the file. But this time, it also doesn't work. It says, I have no idea how to make this work. And if we try and parse the error a little bit, we can see it complains about the equals operator. That's already sort of on the wrong track. It should never do that. But if we scroll up, it gives this. So I'm not using templates here. On line 31, it's complaining, I'm sorry, you've defined a convert vector function that takes a vector of floats. And this one returns a vector of unsigned int. But I'm sorry, the identity of a function, as we recall from week 2, is entirely based on its name and the types of its parameters. And that means you now have two functions that take a vector of float and are called convert vector. And I don't know which one you want. So although I have got one that returns a vector of int and a vector of unsigned int, the compiler can't tell them apart. So why is that? So you can see ambiguating declaration, ambiguating. So the compiler is trying to tell me that if it did this, we would have something that was ambiguous. And we know that compilers do not like ambiguity. So why doesn't this work? It's tempting, and many of you can already see why this is not going to work. But just in case, here is the trap a lot of people might fall into. They would say, well, why can't the compiler figure this out? Isn't it obvious that I'm assigning the result to a vector of unsigned int? So I want to call the version of the function that takes a vector of float and returns a vector of unsigned int. Why can't it figure that out? And the answer is pretty simple. It's the first law of assignment statements. The compiler wants to evaluate the function completely before it looks at the left-hand side. Therefore, the compiler doesn't have enough context to know that you want the version of the function that returns a vector of unsigned int. All it knows is you want the version of the function that takes a vector of float. And there are two functions that meet that criteria. There's this one and there's this one. And that's why this is ambiguating. The compiler doesn't know what you mean. Although you might have context, the compiler doesn't have enough context to know what to do. Okay, so what do we do here? Well, before today, we might want to write a whole bunch of different convert vector functions with different names. That would be pretty clunky to write a bunch of, convert vector to vector of int, convert vector to vector of unsigned int. That would be pretty clunky. Wouldn't it be great if I just had one function, convert vector, given that the logic inside the function is pretty much the same in any case? Wouldn't it be great if I could have one function, convert vector, that would handle converting from any vector, a vector of any type, to a vector of any other type? And it turns out with templates, I can. Except in this case, I have to give the compiler a bit of a hint about what my placeholder types are supposed to be. So what I'm going to do is I'm going to adapt one of these definitions to be templated. and I'm going to use this one. So I'm going to define a template. In this case, I'm going to have two placeholder types. So type name, I'm going to call this output type. I'm going to put the output type first because I guess reading from left to right, the output type is the one I use earliest in the signature. Although in general, it's your choice. There's no requirement that you go from left to right. And actually, whether to go from left to right or not, whether that's logical is sort of, your mileage may vary there. Okay, so I'm going to define a template with two placeholders, output type and input type. I'm going to take a vector whose elements are of the input type, and I'm going to produce a vector whose elements are of the output type. And then here, my output vector will, of course, have element type, output type. And each element of my input type will have, my input vector will have type, input type. Okay, I think I've now created a generalized version of this function, a version that can take vectors of literally anything, because I use a placeholder, and produce vectors of literally anything. And it should work as long as there is a way of converting from the input type to the output type. And that's something that I suppose the programmer calling the function will have to sort out themselves. But I know that, for example, I should be able to convert from a vector of float to a vector of int. Okay, well, I mean, why don't we just hope for the best and try compiling this? And it doesn't work. And so if I scroll up a little bit, we can try and work through the compiler's problem here. So it complains on line 37. And actually, for the sake of clarity, why don't we comment out the other call and just see if we can make the original version of the function, the one we had coming in, see if we can make that one work. Okay, so we try compiling and it gives us 3 errors, or it gives us 1 error and then it tries to show its work. It says, sorry, on line 37, I don't know what you mean by convert vector. There is no matching function for a call to convert vector with a vector of float, which seems a little bit weird because didn't I just write a function called convert vector that can take a vector of anything? And then the compiler tries to explain itself. It says, okay, well, there is a candidate. I could try the one you just wrote. So notice the very long signature here. I could try, let's see, we've got class output type, class input type, convert vector, and it takes input type. Okay, so I could try this one, the one you've defined on line 18, but I wasn't able to. The template argument deduction failed. I couldn't deduce output type. Notice the compiler isn't complaining about input type. On line 37, and again, I'll try and cram everything into one screen here. On line, well, it won't be line 37 when I'm done with it. On line now 30, the compiler is saying, actually, I do understand what input type is. I tried the function on line 18, and I figured out that input type was supposed to be float, because you gave me a vector of float, and the function expected a vector of input type. So I could deduce that input type was supposed to be float. But I couldn't deduce the output type because, again, by the first law of assignment statements, the compiler doesn't know what you want the output type to be. It doesn't have enough context. You need to tell it because it can't deduce that. So here it's saying, I'm sorry, I can see you have a template, but you haven't given me enough information for me to be able to use the template. And we have an option. We are allowed, when we call any templated function, to explicitly tell the compiler what the placeholder types are supposed to be. And we use angle brackets for that and just provide the placeholder types in order. So here, I want the output type to be int, and the output type comes first in my list of placeholders, and I want the input type to be float. And so I provide them both with commas between them, in angle brackets as part of my function call. And we try this, and the error is gone. Because here the compiler says, okay, you want me to make you a version of convert vector with output type being int and input type being float. Great, that's done. And then it does that, it tries calling that version and says this all works. You gave me a vector of float, you assigned it to a vector of int. Everything lines up. And I'll do the same thing down here. So here I would like the output type to be unsigned int, so we write unsigned int. And I want the input type to also be float, because I'm still converting v2. So we call this explicit instantiation of the template. It's a case where you, the programmer, are consciously invoking a template and saying, here are the placeholders I want to use today. You aren't relying on the compiler to figure it out for you. And I'm going to come back to this, to the idea I just brought up of these, what's in angle brackets sort of being a form of parameter in a second. I want to just go back and show another example of explicit instantiation. So we saw in the first example that we could trust the compiler to deduce the placeholder type from the context. So I give you a vector of int and the function wants a vector of t, so the compiler figures out that you actually wanted a you wanted t to equal int. But you are always allowed to use angle brackets. I'm always allowed to explicitly instantiate the template. There are reasons why that can be helpful. One of them is if you're paranoid that the compiler won't figure it out, you can always give it a hint. I think in general it is healthy to trust the deduction process. In cases where it fails, then you need the angle brackets. But all semester we have been using all of these templated functions in the standard library in a way that was sort of opaque. And that's, I think, a good way of implementing abstractions. We don't care exactly what print vector does. We just know that print vector prints our vector. We shouldn't need to micromanage if we don't have to. And we like the convenience of just being able to call these apparently magic functions that can work with any type we give them. Although we now know that all semester, many of those functions that could work with any type, an example being the makePair function, secretly were using templates and type deduction all along. Okay, finally, so what was I talking about with passing stuff in? So I'm calling a function on line 39 called convertVector. And we have known back to 111 that when I call a function, the stuff I pass in the round brackets, those are the function's arguments. And the function's arguments in round brackets are evaluated and passed in when the function is actually called. The function could exist for hundreds and hundreds of lines of code before I call it. At the moment it is called, that is where I compute the values of these parameters and pass them in. Okay, fair enough. That's how functions work. But I just talked about what's in the angle brackets as sort of being a form of parameter as well. And I stand by that. I am defining how the function works by passing data into it. I am providing a certain form of parameters. In this case, the parameters are exotic. They are type names. But it's worth noting, although we're not going to need this in the course, I'm allowed to accept whatever parameter type I want as an argument to a template, as a template parameter. I could in fact add an int parameter as one of my placeholders in the template, and then I could pass it in by passing in the number 6 here or something. I am allowed to do that. In this course, we won't really have any occasion where that's necessary. And you can create you can create your own types that can be accepted as template parameters. So you don't just use type names as the parameters you pass into templates. So instead, I would like to promote, instead of the template being some special thing, I would like to promote the idea that what goes into angle brackets is, in a sense, just another form of parameter you pass to a function. The difference is when the parameter is computed. So the parameters you pass in round brackets get computed and evaluated and passed in when the function is actually called. If I call the same function over and over, every time I call it, I recompute what I'm passing in. On the other hand, what I pass in with angle brackets is also a certain form of parameter that affects the function's behavior, but it gets passed in, it gets computed and passed in when the function is compiled. When you compile convertVector, the compiler goes in and creates for you a customized version of the convertVector function using unsigned int as the output type and float as the input type. So in a sense, these are just parameters that are computed when the compiler compiles the function. And I'm going to expand on this further because there actually are another set of brackets we could use that define, I think, things that get passed in not when the function is compiled, not when the function is run, but when the function is created. Because it turns out functions might be created after compile time. That is actually the main topic we're going to get to 2 weeks from now. And I think it's great to condense those into some grand unified theory of all the different ways we can parameterize a function. And we'll see also that we can use angle brackets and template directives not just on functions, but on types, but on classes and structures. And we might have foreseen that because all along we've been using angle brackets on vectors to define a vector of whatever, not just a vector of int or float, but of any element type that I can copy in, that I can use push back on. And so we'll talk about defining templates on types in the next video.